Well, here's section 11.4, and I think maybe the end is starting to be in sight for some of us now. Our objective today is our cross product of two vectors in space, so we have to make sure we're only dealing with 3 dimensions today, and applications of the cross product. Well, the cross product is another operation type thing that you can do with vectors, and it's used to find a vector. So you'll be actually finding a vector in this situation. It's a vector in space, and it's orthogonal. Remember, orthogonal means that it has to be perpendicular to 2 given vectors. So our problems will start with 2 given vectors, and the idea here is that we want to find a third vector that's orthogonal to the given 2. Definition of a cross product of 2 vectors in space: let U be this vector and V be this vector. The cross product of vectors U and V. So when we're dealing with cross product, it's vector U cross vector V. And this is a really fun formula to remember. It's U sub 2 times V sub 3 minus U sub 3 times V sub 2. And that's times I, basically meaning that's your first component of your vector in space that you're creating. Subtract U sub 1 times V sub 3 minus U sub 3 times V sub 1. Multiply that by J, so that tells us that's our second component in our vector. And now we're adding U sub 1 times V sub 2 minus U sub 2 times V sub 1, and that's times K. So this looks really, really nasty, and it's pretty ugly. Some of you maybe start to recognize what this is, or some parts to it. Yeah, it is really ugly. But there's a trick that will help us do this and not have to apply this formula or memorize things in this way. So keep in mind that this cross product only applies to 3-dimensional vectors. And some of you, like I said, maybe remembered this. A convenient way to calculate your U cross V is to use the determinant form with cofactor expansion. So determinant form, it's the determinant form of our matrices. So what we're going to do is we're going to create this formula up here using a matrix, which is much easier than memorizing a formula. So if you have U cross V, so it's cross product, so we always say it as U cross V, and those are our vectors. When we write it out in a matrix form, we only have our two vectors here, and when we do, in order to figure out the determinant form, we really want to have a 3x3 vector. So we're going to make this I, J, K. And that's just always going to represent the IJK, and that's basically, we get that cofactor expansion there. If U is first, it has to be U sub 1, U sub 2, U sub 3. So your 3 components, they have to go in order. So U has to come first, and then it's cross V, so V sub 1, V sub 2, V sub 3. Well, now what we can do is, if you think back to matrices, if I want my first part of it, basically you're crossing those things off there, and it's I times this determinant of this portion. Well, what you end up getting then is, we'll keep this pretty simple. We multiply, remember U sub 2 times V sub 3, multiply, and then it's minus this cross together. So V sub 2 times U sub 3. And really, within these two parts, multiplication is commutative. So whether you put V sub 3 times U sub 2, that doesn't matter, or vice versa here, that doesn't matter. And this is times I, basically representing our first component. Then it has to be subtraction, so keep that in mind, that this operation is subtraction. And I'm going to erase what I previously had, so you'll get really used to these, and it won't be too bad later. But remember, we take our J, we cross off our horizontal and vertical line. So then we're left with our cross here, and our minus our cross there. So when we write this one out, it would be U sub 1 times V sub 3 minus v sub 1 times u sub 3. And that is times j. So when you set it up, and we'll, like I said, we'll get really good at these where you won't have to cross off things as you go through it. But you cross off vertical and horizontal. That leaves you with the 2 by 2 matrix. This operation is addition. I gotta write smaller here now to fit everything in. And now we have addition. And it's the same thing. You're always doing your cross minus the cross there. So u sub 1 v sub 2 minus v sub 1 u sub 2. I'll scoot this over a little bit. As far as it goes. And then that's multiplied by k. So really, when you look up above, it's just a much more convenient way to set this up. And I guess you can memorize it, but to set up the matrix is really easy. Let's erase those out of there. And going through and practicing a couple of them is, you'll get the hang of it real quickly. So an example for number 8, we're given vectors u and v, and we want to find the cross product. We have 3 different situations. Remember, cross product will always create a vector answer. So for letter A, we want to have u cross v. Therefore, our matrix is I'll give myself a little bit more room, I, j, k. U has to come first. So when I write out my u, I have 3i. I do not have a j. So that's going to make j would be 0 for that second component. And then it would be 5. And then for v, I'd have 2, 3, and a negative 2. Alright, well, we want to figure out our cross product here. So usually what I do is just go like that to start. I just cross them off. And this creates for us 0 times a negative 2 is obviously 0, minus 3 times 5 is 15. And then that's I. Remember here your operation is subtraction. And then we can erase those lines or just draw them in real lightly with your pencil. So for the second term, we go from the j, we make our vertical line and our horizontal line. And we have 3 times negative 2 is negative 6. Operation is always subtracting here. 2 times 5 or 5 times 2, again, their order doesn't matter. That would be times j. And now our operation we have to be adding. Let's see if I can erase this part. So for k, I need my 3 times 3 is 9. Minus 2 times 0 is 0, and that's multiplied by k. And so when we write out, now to write our final vector, we have negative 15i, negative 6 minus 10 is going to give us negative 16. We have a negative of it, and this darn subtraction here gets us a lot. That becomes 16j. And then obviously 9 minus 0 is 9. That's addition at the end, so that's nice. That's just 9k. So here is our cross product. It created a new vector. And remember, this new vector is orthogonal, which is perpendicular to our original 2 vectors. Letter B, the cross product of u cross u. So if we set this up, we have I, j, k. Vector v is first. We have to write it first. So it's 2, 3, negative 2. Vector u is second. So it's 3. Remember, the j is, there's nothing there, so it'd be a 0, 5. Cross product, you have to be in space, so you have to have 3 dimensions. Alright, so I want you to pause this and try and do this one on your own. Alright, so here's your work for it. Writing everything out. Again, be very careful with positives and negatives. And we should have for your answer the cross product, creating our new vector, 15i minus 16j minus 9k. Well, now if you look at the comparison between A and B, u cross v compared to v cross u, you can obviously tell that the cross product is not commutative. So let's write that down underneath here. Cross product is not commutative. Obviously then order is very important, so if u is first, that has to be in the second row. Cross v, v has to be in the third row. And the other thing that we can say instead is that if you have u cross v, we can tell that everything is the exact opposite. So this is equal to negative v cross u. Alright, and then let's do the third one, letter C. And C, looking up above, it was v cross v. Alright, so pause this, and again, you calculate what is v cross v. Okay, so if we have v cross v, v is obviously 2, 3, negative 2, 2, 3, negative 2. As you go through this, every term is going to create 0. So then your answer would be the 0 vector, and that's a property that we'll talk about next. So like I said, once you set up your matrix, it's pretty basic. You do a couple of these things and you understand how the property works really well. And I think setting up the matrix is a lot better than trying to memorize it's this term times this term minus this term times this term. Like I said before, the biggest thing here is remembering that that operation you have to subtract, and then this one you add to get to your third component. Okay. Talking about some properties, algebraic properties of our cross product. If we let u, v, and w be vectors in space, and c is a scalar, so meaning it's just a number, this property we talked about on the previous side. If you have vector u cross vector v, we know the commutative property does not apply, but we can say it's equivalent to the negative of vector v cross u. The second one is if you have u cross v plus w. Well, if you take vector v plus vector w, that's going to create a new vector. So you have the u cross this, which is creating a vector. Well, I think this is probably the most convenient way to do this. You could say that it's u cross v plus u cross w, but that's rather inconvenient to do. Maybe put these things in parentheses here, because it makes you do the cross product twice. Well, it's much easier just to add these two vectors together, because vector addition is very easy. Just adding your first components together, your second components, third components, and then you only do the cross product once. So this way seems a lot more logical, but you could do this if you wanted to. If you had a scalar and you multiplied it, and it's that scalar times u cross v. Again, you could take this scalar and say, well, I'm going to multiply that scalar times u right away. Maybe that's really easy to do. And then you can take that new vector cross vector v. Or you could say it's u cross that scalar times v. So really you can multiply this to either one, but you can't multiply it to both. It would only go to one of them. If you had u cross your 0 vector, that will always create a 0 vector. Another property is if you have vector u cross vector u, just like we did on that last example on the previous page, the third example. If you have u cross u, we did v cross v. This will always create 0. And then the last one, dealing with the dot product, if you have vector u dot vector v cross w. So here you'd have to create this vector using the cross product, and then use a dot product between the two. This, you could say, well, it's the same thing as u cross v dot vector w. So I don't use too many of these. I guess if I use any, I use the first one, the fifth one. Those are kind of the ones that we talked about. But these are other algebraic properties that go along with vectors and our cross product. Geometric properties of our cross product. These are going to be used a little bit more. And u and v, again, they're non-zero vectors in space. And theta is the angle between vectors u and v. Well, if you find u cross v, this is basically goes back to the definition, but it does deal with geometry. U cross v is going to create another vector. We know that. And this vector is orthogonal to both u and v. So u cross v is orthogonal, or perpendicular, to both vector u and vector v. And if u cross v, if u cross v is equal to 0, this happens if and only if u and v, so vectors u and vector v, are scalar multiples of each other. So our scalar multiples of each other. What this means, and remember, if they're scalar multiples of each other, it means that your two vectors, your two original vectors, are parallel to each other. So if u and v are parallel to each other to start with, then you'll have the cross product will equal 0. Another geometric property that we end up using is if you take the magnitude of the vector that you create when you use the cross product. So cross product creates a new vector. I'm going to take the magnitude of that vector. This is going to equal the area of a parallelogram. So equals the area of a parallelogram having u and v as adjacent sides. I was put in parentheses. U and v are adjacent sides. So this is one that we end up using quite a bit because it allows us to solve for area. And another one that you could use, and I like to use this because I think it's so easy. Cross product is easy. Magnitude of a vector is easy. But u cross v, which obviously represents the area of a parallelogram, it is also, you can calculate it as the the magnitude of vector v. The magnitude of vector u just times the magnitude of vector v, because the magnitudes are going to be just constant. So you're multiplying those two numbers together, times sine of theta. Remember up here it said theta is an angle between vectors u and v. So you could go and find what is the angle between them, and then sine theta. But personally, I like to use 3, this property, much more, just to say, well, hey, the magnitude is equal to this. I guess it could allow you to solve for an angle if you need it to, but when I talk about area of a parallelogram, I'll just say take the cross product and then take the magnitude of it, instead of having area of a parallelogram and doing this operation, or this formula. Okay, so a couple examples now. Number 16. We have to first of all find, let me go back a little bit. Find u cross v, so that'll be part A. And show that's orthogonal to both u and v. So that would be part B. A, finding u cross v. We have I, j, k. U is first. Remember, they're not commutative, so we have 1, 6, 0. V is second, -2, 1, 1. And going through this now to figure out what our vector is, you can just write it in component form right away. So you can say, all right, I have 6 minus 0. So that's 6. This second term, remember, you're subtracting, so I always put in a negative. And if my answer is negative, well, then I just make it a plus. So it's super easy to deal with, but I have to remember that this is negative. So if I look at the second one, we'd have 1 minus 0, so that will give us -1. Our third thing, remember, we added it, so we really don't have to worry about it. And then I just go like this. That will give us 1 minus a negative 12. So 1 minus a negative 12 will give me 13. So there's our cross product, creating a new vector, 6, negative 1, 13. Now B, we have to show that it's orthogonal. So to show that it's orthogonal, what we can do is, if we go back up to our properties here, I thought that one of these said where they're going to be orthogonal. I thought I wrote it down somewhere. Let me check. Okay, I didn't write it down anywhere. If we have to think back to our previous section. So if we have two vectors that are orthogonal to each other, remember, and we'll just put a little note over here for orthogonal. It said that if you have cosine of theta was equal to u dot v divided by, I think it was the magnitude of u times the magnitude of v, if the dot product is equal to 0, then we know that they're orthogonal. So that goes actually back to the last section where this was written. So the dot product between our two vectors, if that's equal to 0, then we know they're orthogonal. Remember, if you have the dot product between two vectors and it's equal to they're equal to the same, like to check if they're parallel, then they'd have the same scalar multiple there. So for B, what I want to do is to show that u and vector u and my new vector, to show that they're orthogonal, is I want to use the dot product. So I have I have 1, 6, 0, the dot product of this new vector that was created. So 6, negative 1, 13. And if I look at that dot product, remember you multiply your terms together, so it'd be 1 times 6 is 6, plus 6 times a negative 1 obviously is negative 6, 0 times 13 is 0. Yes, that's equal to 0. The dot product between our two vectors, if it's equal to 0, we know that it's orthogonal. So check, that one is orthogonal. Got to squeeze this one in. Our other vector, negative 2, 1, 1. Dot vector, the new one that we created, 6, negative 1, 13. Negative 2 times 6 is negative 12. 1 times the negative 1 is a negative 1. 1 times 13 is 13. That's equal to 0. Yes, those two vectors are also orthogonal. So dot product between two vectors, if it equals 0, we know that they are orthogonal to each other. Number 32. Verify that the points are the vertices of a parallelogram and find its area. Well, our points, this would be A, B, C, and D. So if our parallelogram right now, if these are vertices at A, B, C, D, and they go in that order, what I want to show is that for a parallelogram, side AB will have to be parallel to side CD. So we can go in order and just say, what is AB going to be? And let's create that vector. Vector AB, well, 6 minus 2 will give us 4. 5 minus a negative 3 will give us 8. Negative 1 minus 1 will give us negative 2. Then if we just keep going in order and say, well, what's vector BC? That would be the next side. So like here we would have A to B. Here we would have B to C. So B to C is really no relationship between vector BC and vector AB. So B to C, we'd have 7 minus 6 is 1, 2 minus 5, negative 3, 2 minus a negative 1 would be a positive 3. Now when we go to vector CD, to go in order, if we want to show that that AB is parallel to CD, so I'm going to erase the picture up here, but then we have CD, vector CD, 3 minus 7, negative 4, negative 6 minus 2, negative 8, 4 minus 2 is 2. And then are these two vectors parallel to each other? Yes, because they have a scalar multiple of -1. So if we're showing that it's a parallelogram, this is really good. So parallel, yes, whoa. I'm just going to put yes and scalar together. Miss the S, I'm not really sure. Scalar is equal to -1. And then we'd have to go on and say, well, what is D to A, vector dA? So 3 minus 2 is 1. -6 minus a -3 would give us -3. 4 minus 1 would give us a +3. So obviously these two are parallel to each other. So parallel, yes. So we definitely have a parallelogram. Now we want to find its area. Well, if we go back to our geometric properties, to find the area of a parallelogram, it's the cross product of your two vectors, and then you take the magnitude of it. So pretty easy here. Your two vectors, though, remember, have to be adjacent to each other. So we would have I, J, K, and I'm just going to start with vector A. B is 4, 8, -2. Then we're just going to go to BC. So 1, -3, 3. And in the long run, I want the magnitude of this vector that I create, which would be 24 minus 6. So that would be 18. Remember, now we have to make this middle term a negative. And that would be 12 minus a -2. So 12 minus a -2, and if you have to write it out, write it out. That would give us 14, but remember that middle term is negative, so that's a -14. And then our last one, for K, we would have, it's -12 minus 8, which is just giving us -20. Alright, so take the magnitude of this, and our area then will equal, we need to get 18 squared plus 14 squared plus 20 squared. And we don't have to worry about the negatives. Obviously, to create the proper vector, yes, but when we have magnitude, remember we're squaring, so just make it positive. And this should be the square root of 920, which is approximately 30.332, and then its area, so it's units squared. So area of a parallelogram. Pretty basic things there. Going on to another example, number 34. We want to find the area of a triangle, and our triangle, it's in space, so we have our vertices 2, -3, 4. And I'm just going to say that this is going to be A, here's B, here's C. So we want to find the area of this triangle. Well, here are our vertices, so we're just A, B, C, and it's really nice that they give us this hint. So our hint here is that if we take 1/2 the magnitude of the vector that we get with U cross V, it's the area of the triangle, and U and V just has to be adjacent sides. So basically we're taking our parallelogram, take half of it, yeah, that's going to be obviously our triangle there. So pretty common basic idea here. I think it would probably best just to create, what is that vector AB? Write it down so you get your adjacent and you don't have any mistakes. 0 minus 2 will give us a -2. 1 minus a -3 would give us a +4. 2 minus 4 is going to give us -2. And then an adjacent side would be BC. Well, in a triangle, all sides are adjacent, so we don't have to really worry too much. But for BC, -1 minus 0 is -1. 2 minus 1 is going to be 1. 0 minus 2 is -2. Well, now for a triangle, still use our cross product, IJK, -2, 4, negative 2, negative 1, 1, negative 2. And from here, now that we have it set up, which is pretty basic common sense, why don't you pause this and figure out what the area of your triangle is going to be. Here is the work shown for it, and so I went through, created my vector, cross product obviously, and then took the magnitude. So square root of 44, approximately 6.633 units squared. And I hope that answer is right, because on my notes that I had, I found an error that I had, and so this is obviously different, but I found an error. I hope everyone agrees with me. Otherwise, it's good conversation to figure out where my mistake is, because obviously we know those things happen too. Okay, so next we have triple scalar product. So now we have, for vectors u, v, and w in space, we have our three vectors. The dot product of u and v cross w is just how it sounds. It's u dot v cross w. So we have to do this cross product first, because once you do the dot product, it has to be between two vectors. So I'd recommend do this cross product first, and then take the dot product between u and your resulting vector that you have. So I guess I should go back. That's what we could do if we have a triple scalar product, and this is used in some specific applications, which we'll see. We have, for B, here's vector u, here's vector v, here's vector w. Well, then our triple scalar product is given by, so that u dot v cross w, we can get an answer right away without having to do the cross product and then do the dot product with it. If it's in this specific order, remember order is important, it's u sub 1, u sub 2, u sub 3. Because really that's just going to multiply this cross product by these values, which is what we want. And then so v sub 1, v sub 2, v sub 3, and w sub 1, w sub 2, w sub 3. So this idea allows us to right away just calculate it without having to do the cross product, because if we have a u, remember that the dot product just says it's our first term, of this vector times the first term of the vector that's created, or the second vector. So this is a really nice way to show this, and to calculate it very quickly. A couple things here. The value of the determinant is multiplied by -1 if you interchange two rows. So the value of the determinant is multiplied by -1 if two rows are interchanged. So if I just switched obviously two rows around, I can switch rows v and w, or I could switch rows u and v, but then my value is going to be multiplied by a -1. If all three rows are interchanged, the value doesn't change. If all three rows are interchanged, the value doesn't change. So obviously if u is in a different spot, v is in a different spot, and w is in a different spot, your value isn't going to change here. Well, what this can be used for is to find, for C, the volume of a parallelepiped, which is a polyhedron, all of whose faces are parallelograms, with u, v, and w have to be adjacent edges. Well, to find this volume, it is the absolute value of u dot v cross w. So really it doesn't matter the order, because we're taking absolute value. And if we look up here, the determinant is multiplied by a -1. So you're going to get the right answer as long as you take the absolute value of it, which is really nice. And so this, remember, we can't get screwed up here. When you just have the single bar, that just means absolute value. We're taking the absolute value of this dot product. So for an example, 46, use the triple scalar product to find the volume of a parallelepiped having adjacent edges U, V, and W. Well then, our volume is, we just create our 3x3 matrix, 1, 3, 1, 0, 6, 6, negative 4, 0, negative 4. And your order doesn't matter because when you take the absolute value, it's going to be positive no matter what, which it better be because it's volume. So instead of multiplying by I, you're multiplying by 1. And that helps deal with the dot product without actually having to do the cross product and then the dot product. So you have 1 times, you'd have negative 24 times, or negative 24, sorry, minus 0, so negative 24. Your second term is negative. So when we look at our second term, it's going to be 3 times, you'd have 0 times a negative 4, so that's going to be 0, minus a negative 24, which gives us 24. Then we add, here we have a 1, and then we'd have 0 minus a negative 24, which is 24. So when we calculate this, we have negative 24 minus, that would be 72. If we add then 24, obviously those two could simplify out, and we'd have negative 72. Remember up here it says it's the absolute value, so really we could throw absolute value around everything. Typically what I just do is at the end I say, it's the absolute value of my answer, which we're finding volume, it's 72 units cubed. So I don't like to particularly write all these absolute values, but you have to know what the context of the problem is, and we're finding volume. If you switch the order then of your 3x3 matrix, it doesn't matter. If you switch the order, some of you, if you interchange just 2 rows, you'd end up getting a positive 72 for your answer. Alright, and number 48, find the volume of the parallelepiped with vertices at 0, 0, 0, 1, 1, 0, 1, 0, 2, blah, blah, blah. Well, what we have to do is make sure that the vertices that we choose, we have to create them into vectors, and they have to be adjacent to each other. So I start with the simple one, like 0, 0, 0, and we know that if we have 0, 0, 0, and maybe set up, like our next one would be 1, 1, 0. So that would be a 1, a positive 1, and 0. So that would make that line. Well, now we have to make sure that all 3 are adjacent to each other. So we have 1, 1, 0. Well, the next one I want like this point again because it has to be adjacent, but we like being right at the origin or at the pole, the origin. So 0, 0, 0. We have to figure out what is this, because they have to be adjacent, what is that point? Well, if we look at that one, to try to figure out what is this thing going to be, I would say it's 0, a positive 1, 0, 1, 1. And that will get me to that point. So 0, 1, 1. And then our last one, we have 0, 0, 0 again, but it has to be this point specifically here for it to be, I think that's the right one, for it to be adjacent. So it'd have to be 1, 0, and then it must go up 2. So it'd be that point. And so with the picture, you have to make sure that you choose adjacent sides. Now you have to create a vector. Well, the vectors between them are pretty easy. So you have vector 1, 1, 0. And this vector is super easy because one of your vertices is at the origin. So then we'd have 0, 1, 1, and we'd have 1, 0, 2. Now we can take our matrix 1, 1, 0, 0, 1, 1, 1, 0, 2, And to calculate what this volume is, we have 1 times 2 minus 0, so that would give us 2. Our second component we have to subtract here. We have 1, because it's a 1, times it's 0 minus 1, so that's a negative 1. And the last one is awesome because it has a 0 in it. So really it's 0 times, we don't even care, that doesn't matter. And this would give us 2, and then we have, that would give us a positive 1. So that's 3 units cubed for our volume. The volume of the parallelepiped. But the thing is, you have to make sure that you can find and make sure the points are correct to have adjacent sides there. Alright, the last thing that we have is torque. And for our torque, it's a moment or moment of force. In physics, the cross product can be used to measure torque. So torque is the tendency of a force to rotate an object about an axis, a fulcrum, or a pivot. So think of this, we are rotating an object. Just as force is a push or a pull, torque can be thought of as the twist. So you're not just pushing or pulling, you're actually twisting on it with it as well. So that will create torque. I like the loosely speaking, I like the definitions for the dumb for me. Torque is a measure of a turning force of an object such as a bolt. So for example, pushing or pulling on a handle of a wrench, that's going to be measured in torque. Or whatever, that loosens or tightens the nut or the bolt. So if the point of application of the force is Q, so here's our point of application of our force, the moment of F about P, and we'll look at an example of how this works out. The moment of F about P is given by this. So moment is equal to vector PQ. So here's vector PQ cross vector F. So obviously cross product is between two vectors, and once we look at this with a actual situation, it does get a lot easier. So a vertical force of 50 pounds is applied to the end of a 2-foot lever that's attached to an axle at a point P. So here's our point P, a 2-foot lever. Obviously this is going to be like a twist to it, or the kind of motion that we needed. Find the moment of force about the point P when theta is equal to 60 degrees. Well, we have to create our two vectors for this. We need vector PQ. So basically, what is this vector going to be? And then we need vector F as well. So to start, vector PQ, this one, it's given to us with an angle, and really this X is meaningless to us right now because we can look at it on just our YZ plane. One thing that we do have to take into account that it is a 2-foot lever. So it would be 2, and then times our vector would be 0. It's cosine of 60 degrees, sine of 60 degrees. So I think of it as it's cosine of 60 because y, like x is basically out of the picture for this situation. And so y is your first coordinate that you're dealing with here, and that makes that cosine. Usually we say, well, y deals with sine, but since x is out of the picture, cosine is going to be with y because that's your first coordinate that we're dealing with. So in this situation we can say, well, this is 2, and cosine of 60 degrees is, what is that, square root of 3, 1/2, that should be 1. And then, whoa, totally a mistake. 2 times 0 is 0, so we better go back and put that one as 0. Cosine of 60 is 1/2, times 2 will give us 1. That's a little bit better. Sine of 60 is square root of 3 over 2, times 2 will give us square root of 3. So here's vector PQ, representing basically the lever, the wrench, or whatever you have. And then we need our force. Well, we have to write this vector, this force, in a three-dimensional sense. Well, again, we don't have an x, so we're going to call that 0. And this is really just going straight down, where our y's go to the left and to the right. So our y is going to be 0. And because you have a force of 50 pounds, but this 50 pounds is pushing it down, that would be a negative 50 for our force. Obviously, if it were pushing it up, it would be a positive 50, but because it's going straight down, we're representing this vector. All you're doing is going down, and that would just represent the like the z component, or the z factor there, I guess. So in these situations, then, the formula, like we said up above, you can see a little bit, that to find the moment of this force, our moment is just vector PQ cross vector F. So to create what this is going to be, we can go back IJK. We have 0, 1, square root of 3, 0, 0, negative 50. I like that there are a lot of zeros. It makes it a lot easier. What we create for our first term here would be negative 50 times 0. So there's negative 50. Our second, remember it has to be a negative. We'd have 0 minus 0, so that's awesome. That's 0. Then erase that negative. And for the third, it's positive. And it's nice because we have 0 minus 0, 0. So now that we created our new vector, we want the magnitude of this to represent our torque. So the magnitude in this situation is going to be 50 foot-pounds, because it would be taking that negative 50, squaring it, taking the square root. Great, you're left with 50 foot-pounds. So that's section 4, all in one recording, which is maybe a first in a long time. And the homework for this section, not too many problems. Page 796, 1, 5, 7, 11, 15, 29, 31, 35, 37, 43, 45, 47. But in number 31, it's most convenient if you switch the last two coordinates around. It'll make it be then like going from A to B, B to C, etc. So that makes a lot more sense. For number 31, switch your last two coordinates, and it makes the problem a lot easier. Good luck with this, and really section 5, I think this chapter actually gets easier as we go on here. The last couple sections there's not so many weird, like with the word problems aren't so weird like this whole torque thing. So good luck with it.